So this is the second part of molecular structure and bonding, where we're going to revise VSEPR theory and just explain a few things and extend a bit of your knowledge from first year. So remember what VSEPR theory is. It's a theory or a model that provides a method for predicting the shape of molecules based on electron pair repulsion. Okay. It gives the approximate shape of a molecule, and you'll remember that from first year, you remember that you've got for 2 electron regions, the arrangement is linear, 3 is trigonal planar, 4 tetrahedral, 5 trigonal bipyramidal, and 6 is octahedral. And within the tetrahedral, the trigonal bipyramid, and octahedral, you've got some other geometries as well, where we looked at description of the molecular shape. And remember that the electron domains are different from the geometrical domains. So the theory revolves around the fact that obviously electrons are going to repel one another, but quantum mechanics forces them together as bonding or lone pairs. But all of these pairs repel each other. So the molecules then must adopt geometries in which the valence electron pairs position themselves as far apart as possible. Now, in this instance, we generally describe molecules with a general formula. And in this case, the A would be the central atom. Okay, so we've got a central atom over here. Then the X are the atoms that are bonded directly. So they'll have covalent bonds, all right? So it's bonded electrons, usually as covalent bonds. And then these guys here will be the lone pairs. So that's the formula. So we have the central atom, the bonded atoms, and then the lone pairs of electrons. Now, obviously, there's going to be a certain number of atoms bonded. So that's what M represents. And N will represent the number of lone pairs. Okay. And if we add M and N together, we get something called the steric number, which I'm going to represent as Sn. Okay, so there are then obviously a total number of positions around the central atom is also then the steric number. So if we have, let's say, 4 atoms plus a lone pair of electron, then the steric number is going to be 5. Okay, so this then leads to differences between the electron domain geometry and the molecular geometry valence. Okay. Now, if we had a look at what we are familiar with from first year, you will see that some examples given for linear geometry, we get carbon dioxide. For trigonal geometry, trigonal planar, we have the sulfite. The other one is nitrate. Tetrahedral geometry is given as methane. This is where the electron domain geometry and the molecular geometry is the same. Okay, so I'll leave you to have a look at these examples. And now at this level, in second year, we introduce a bigger steric number 7, which you probably haven't seen before. It's called pentagonal bipyramidal. Okay, so here you can see the pentagon shape. It's a 5-sided figure, so there's 1, 2, 3, 4, 5. And then we've got an apex, which will give us a pyramid like this, and another apex, which will give us the bottom pyramid like that. And that's where we get pentagonal bipyramidal. And then the last one is a steric number of 8, where this mostly applies to elements at the bottom of the periodic table. So here we've got tantalum, and you can see it's got 8 atoms joined, coordinated to its center, and it's called square antiprismatic. So you can see there's like an upside down pyramid on this side of the tantalum atom, and then you've got another pyramid underneath. Okay, so that's called square antiprismatic. These molecules these arrangements are pretty rare, but they are evident. Okay, so what does lone pair repulsion do? Okay, if we looked at lone pair repulsion, let's have a look at the tetrahedral geometry. So the electron domain geometry is 4. Okay, so in this case, the electron domain geometry and the molecular geometry is both tetrahedral. All right, and we know that for the angles between atoms, so if we looked at this bond angle here, we see that the angle is 109.5 degrees. All right, now a lone pair is going to occupy much more space. So what's going to happen is you're going to see that you're going to get this huge space of electron density around ammonia. Okay, ammonia has an electron domain geometry of 4, okay, because we've got a lone pair and then we've got 3 bonded atoms. So this will have the formula AX3E. Okay, so that's what we would have a look at here. And in this case, because this lone pair is sitting way on the top here, we get a decrease in the angle to 106.6 degrees. You would have learned about this in first year, that the angle decreased to 107 degrees, but the accurate value is given there. Now, what happens when we have 2 lone pairs? Okay, now we even got a bigger issue because we've got 2 lone pairs which are hugely repulsive to one another. And so the angle is going to change to 104.5. And in this case, if we had to write the general formula, the electron domain geometry is still tetrahedral, but the molecular geometry in this case is now bent. So this becomes AX2E2. Remember, A is the central atom, so that's the oxygen. X2 refers to the 2 hydrogens, and E refers to the 2 lone pairs. Okay, so here we have the tetrahedral geometry at the top. So this is tetrahedral. This one, we've got the trigonal pyramid. Okay, remember this from first year. So this is trigonal pyramid. And this is either the angular or the bent. All right, so that helps us to understand what happens with the tetrahedral geometry. Now, let's go a little further, where we're going to look at the electron domain geometry for trigonal bipyramid. Okay, the general formula is AX4E. Okay, in this case, that's the one we're going to look at. Usually, electron domain geometry, if all of the positions around the central atom had bonds, it would be AX5. But in this case, let's look at one lone pair. And where is the best place to position this particular lone pair? There are a number of positions. Obviously, let's talk about what the names of these positions are. So if this is the central atom A over here, this position at the top here is called the axial position. So I'm going to label it A and I'll write it at the top here. This is an axial position. And then the positions of these atoms, this atom here, is at something called an equatorial position. So these are equatorials, and that would mean that this lone pair of electron is on the equatorial. Why do we say equatorial? Well, it's like the world. We have an equator that goes around the center. Okay, so that's where the word equatorial comes from. Now, we've got 2 possible locations for one lone pair. All right, we can put the lone pair either here in diagram A on one of the equatorial positions, and it doesn't matter where you put it. You can put it here, you can put it here, or you can put it here. It really makes no difference because it's in the same position. If we looked at it, if we turned it the 120 degrees, each way this molecule would look the same. Okay, or we could place the lone pair of electrons on one of the axial positions here. Okay, now what does VS-EPR theory tell us? Remember what the definition is. It says it must be electron pair repulsion And there's a corollary to this in that it must have the least amount of interactions possible. All right, so let's look at diagram A. You will see that diagram A, where the lone pair is sitting here, okay, so here's the lone pair, there are only two possible interactions for this lone pair to affect the rest of the molecule. So those are indicated by the green arrows. So there's going to be an interaction between this bond pair here. Okay, remember that these are bond pairs. So this is an atom, a central atom bonded to something. And this is a lone pair. So there's a lone pair bond pair interaction. I'm going to write it here. Lone pair bond pair. Okay, and there's another one over here. Lone pair bond pair. Okay, and in that sense, that means we have two lone pair bond pair interactions. All right. But in this instance, if we look at diagram B on the right-hand side here, you will see that if we place the lone pair of electrons right over here, if we place it in the axial position, we now have three interactions where we have three, there's a lone pair, you can count the number of arrows, so each arrow is a lone pair bond pair interaction, and we have three of them. So we have three lone pair bond pairs, and here we have two lone pair bond pairs. And of course, because we want the least amount of interactions, this one here will be the most energetically stable configuration and geometrical arrangement for a lone pair, one lone pair, to be in this electron domain geometry. Okay, so the least amount of interactions are preferred, as I said. Lone pair interactions are way more stronger than lone pair bond pair interactions. And also interactions with 90-degree angles are important. Larger angles have a less of an influence. So as I've said to you, this interaction here where you have this 90-degree angle, there's a 90-degree angle here, and there's a 90-degree angle here, and we've got two lone pair bond pairs. This is the one that's preferred, lower in energy. This one, even though there are 90-degree angles here, there are three 90-degree angles, but we want to have the least number of interactions. That's the first prize that where we're looking at with least number of interactions. Okay. Let's now look at the second possibility, because this particular electron domain geometry allows us to consider the possibility of having two lone pairs of electrons. Okay, so we have three bonded pairs. So let's look at the picture down the bottom. The central atom is represented by this big blue-green atom, and then these guys here are the bond pairs, okay, and then the purple ones are the lone pairs. All right, so we have this general formula here, which is AX3E2. Okay, there are three locations for the lone pairs to go onto, and obviously the least amount of interactions are preferred in this instance. Okay, so what we need to look at is we need to try to understand how it is that these lone pairs arrange themselves. All right, so where are the possible arrangements? Well, we can have two axial arrangements here and here. We can have one equatorial and one axial here, and we can have one both equatorial. So those are the possible arrangements that we can have. Obviously now, which one is the most favorable? Okay, and this is quite tricky, because looking at this lot, you would think, well, automatically if we put them both axial, they're the furthest apart. But no, actually, remember that this is a lone pair and these are bonding pairs. So we've got 1, 2, 3 lone pair bond pair interactions here, and 1, 2, 3 lone pair bond pair interactions here. So there's actually 6 interactions here, but we want the least amount of interaction. So let's see how we're going to do this. Okay, All right, so remember that lone pair interactions are more important and actually preferable than lone pair bond pairs. Okay, and then interactions with the 90-degree angles are important, and larger degree angles have less influence. All right, so we have the possibility, and we need to remember this, I'm going to put this in order, that lone pair is much more important than lone pair bond pair, which is much more important than bond pair. Okay, so now we need to look at these three diagrams on this slide and decide for ourselves which one is the most preferable. All right, so if we looked here, the lone pair is 180 degrees apart, so the angle is great, but there are too many interactions. Remember the first rule should always try to hold. We've got 6 lone pair bond pair interactions. Where do these come from? Well, there's one, and there's one, okay? And then there's one, and there's one. So if you count the number of lines that I've drawn, you will see there were 6 interactions. Okay, in this instance now, the second diagram in the middle, we've got the lone pair at 90 degrees, and there are 3 lone pair bond pair interactions, okay? And 1 lone pair interaction. All right, so this is a possibility, okay, but we really want them as far apart as possible. So even this 90-degree angle, they're a little too close. But let's look at this third one on the right-hand side. The lone pair is 180 degrees apart. So that means they're as far apart as they can possibly be. And yes, there are 4 lone pair bond pair interactions, but this is actually the most energetically stable, even though we've got lone pair bond pairs, all right? It's the angle between them. They are the furthest apart from one another, so we actually do want that, okay? And even though we've got 1, 2, 3 interactions there and 1, actually, guys, I think there's a mistake here. This should actually be 2 lone pair bond pair interactions. Let me just erase some of my interactions here. So I just want to get rid of all of these interactions. And let's just take a look at the fact that if we looked at this lone pair here, okay, so it has 1 interaction here and 1 interaction there. That's a lone pair bond pair, and this one here is a lone pair bond pair, and this one here is a lone pair. Okay, so there's 3 interactions in total. There's 1 lone pair and 2 lone pair bond pairs, and that will apply for this atom as well. Okay, if I just change the pen color quickly, you'll see what I'm talking about. So we've got this lone pair bond pair, so that's a lone pair bond pair, and then this one interacts with this one as a lone pair bond pair interaction. Okay, so we've got 2 lone pair bond pair interactions from each one, which essentially makes 2 lone pair bond pairs for the red interactions and 2 lone pair bond pair for the purple interactions, and then in total we end up with the 4 lone pair bond pair interactions for the 2 lone pairs, with the lone pair spaced as best as possible. So essentially this one here is the most energetically stable. Okay, so if we have a look at some of these examples that are given, you will see what happens. In the case of the linear molecule, the lone pairs are as far away as possible as they can get from one another. And in this case here with steric number 3, the lone pair can go in any one of the positions. The angle will change. We know what happens with the tetrahedral geometry. I've just explained what happens with the trigonal bipyramidal geometry, where we put the lone pair in the equatorial position, again in the equatorial position, and again here in the equatorial positions, because they're spaced the furthest apart. And similarly, for when we're looking at octahedral electron domain geometry, in this case, we find that the axial position is where the lone pair is best positioned, and here on the axial position, they are the furthest apart. Okay. Let's have a look now at double and triple bonds. They have much greater repulsive effects than the single bonds because of the additional pi electrons. And we treat them as if they were lone pairs. Because they occupy more space, they're going to squeeze the rest of the molecule together. So a lone pair and multiple bonds are going to compete for space when in the same molecule. So let's just quickly have a look at some of the examples. And you can see the position of where the double and triple bonds can actually go. They are the furthest apart in many of the examples that are given on this slide.